なんかバックグラウンドノイズが入ってるみたいなんですけど、これはどうしようもないのかな。ちょっとなんでこのファンが鳴ってるのがどうしようもないみたいなんで、ちょっとそれはいずれ解決します。それで、このサスキンドのクォンタムメックの第2回ということで始めたいと思います。このブルーキャットのページ、あるいは、コンパスに行っていただいて、コンパスのページ、どちらも古賀先生で登録してますので、これですね、この古賀先生でツイッターを探していただくか、コンパスを探していただくか、ブルーキャットを探していただければ、見つかりますので、次回の、開催日時は一応この3月1日の13時ということで回答いただいたので、次回は3月1日明日13時からやりたいと思います。この配信が終わったら、コンパスブルーキャットのページを、書き換えて、それからツイッターにも出します。あと今晩もまだ可能ですので、もし希望があれば、2月28日月曜日21時からという枠でやりますので、お知らせください。このツイッターに私古賀先生をメンションしていただくか、あるいは、これどうなってるのかわかんないな。YouTube がちょっと見れてないんですけど、YouTube を見て、あれYouTube に、これをやるか、あるいは、ここのこれどうなってるのか YouTube のチャットのとこに、要望を入れていただければ OK です。YouTube を見て、視聴は1人だ。いいのこれ。視聴1人。これをスタジオにすればいいのか。あれスタジオじゃないのこれか。これか。これ見えないんですね。なぜか。これ見えなくていいのかな。よくわかんないな。ちょっとわからないので、このまま進めます。はい、それで、こっちのブルーキャットでも、テキストがここでギガファイルの中にありますので、これをダウンロードしてください。それで、どこから始めるかというと、ここからやります。Integration by Parts っていうところからやります。で、これは部分積分ということで、Before discussing linear operators, we will take a short detour to remind you of a technique called integration by parts. It's fairly simple and indispensable for our purposes. We will be using it again and again. Suppose we take two functions f and g and consider the differential of their products fg. We can write dfg equal fdg plus gdf or dfg minus gdf equal fdg. taking the definite integral gives us this way. You just take integral over above, just this way. You take integral, you just put this, and you obtain this equation for integration by parts. Then you will see Fg minus, I think you all know this, 微分積分. Okay, so let me see. So we go. This is the standard formula that you may remember from calculus. But in quantum mechanics, the limits of integration tend to span the entire axis, and our wave functions must go to zero at infinity to be properly normalized. Therefore, the first term of this expression will always evaluate to zero. With that in mind, we can use a simplified version of integration by parts. ここはもう量子力学で考える限り、これは無限の極限ではゼロに行くし、マイナス無限大の極限でもゼロに行くと。で、量子力学はそういうことなので、ここ A と B っていうのはマイナス無限大から無限大。ここもマイナス無限大から無限大。ここもマイナス無限大から無限大っていうふうに、なるケースがほとんどなので、量子力学の場合、そうするとここの最初の項は、ゼロになっちゃうと。ゼロになると。そうすると簡略した、部分積分の公式ができますと。それは、これですと。f dg dx integration from minus infinity to infinity equal minus df dxg integrate minus infinity to plus infinity. This form is correct as long as f and g go to zero appropriately at infinity so that the boundary term becomes zero. boundary term はこの最初の項。消してあった最初の項が boundary term. boundary term become zero. You will do yourself a big favor. You will do yourself a big favor if you just memorize this pattern. Switch the derivative from one factor of the integrand to the other at the cost of a minus sign. So こっちの you take derivative here. Now you switch this way. So then your plus sign become minus sign. That's the equation. Okay, so the next section is 8.1.4 linear operators. Bras and cats are half the story in quantum mechanics. Bras and cats are half the story in quantum mechanics. The other half is the concept of linear operation and in particular Hermitian operators. This raises two questions. What is meant by a linear operator on a space of functions? What is meant by a linear operator on a space of functions? What is the conditions for a linear operator to be Hermitian? What is the condition for a linear operator to be Hermitian? The concept of a linear operator is simple enough. It's a machine that acts on a function and gives another function. Okay. When it acts on the sum of two functions, it gives the sum of the individual result. When it acts on a complex numerical multiple of a function, it gives the same multiple of the original function. In other words, it is surprise linear. これわからないかな。So if you have some linear operator, like operator, if this is something like this, so this operator operates on some multiple of complex number to the function. So this is also complex number. So this is linear. So if you multiply by complex number c, the result is also multiplied by the complex number c. This is linear. Let's look at some examples. One simple operation we can perform on a function psi x is to multiply it by x. That gives a new function x psi x, and you can easily check that the action is linear. We will represent the multiply by x operator with the symbol large X. By definition, then large X psi x equal x psi x. So this action is linear because if you put multiplication c, you see this is the right hand side is also multiplied by c. Here is another example. Define d to be the differentiation operator. That means dx, d psi x is d phi x dx. Excuse me. D phi x dx. So this is also a linear operator because you see here, if you put c here, then you will have c here. So that means c times d psi phi x, d psi x dx. So this is linear. This, of course, is a minute subset of the possible linear operators that can be constructed, but we will soon see that x and d play a very central role in the quantum mechanics of particles. Now let's consider the property of hermiticity. Property of hermiticity. This is in Japanese エルミート性。A convenient way to define a Hermitian operator is through its matrix elements. By sandwiching it between a bra and a cat, you can sandwich an operator L in two different ways. Psi L phi or phi L psi. In general, there is no simple relation between these two sandwiches, but in the case of a Hermitian operator, for which, by definition, L だが equal L. So, this is like Hermitian. Hermitian conjugate. Conjugate. こうだっけ conjugate. Anyway, conjugate, a little bit strange. Anyway, Hermitian conjugate is equal to itself. There is a simple relation. The two sandwiches are complex conjugate of each other. Psi L phi equal phi L psi complex conjugate. Let's see whether the operator x and d are Hermitian. Recalling that x psi x equal x psi x, and using the inner product formula, equation 8.2, we can write psi x phi equal this. And phi x psi is this. Because x is real, it's easy to see that these two integrals are complex conjugates of each other. Sorry, this was wrong. This was complex conjugate. Complex conjugates of each other, and therefore that x is Hermitian. What about the operator d? In this case, the two sandwiches are this one, psi d phi, and phi d psi. To determine if d is Hermitian, we need to compare these two integrals and see if they are complex conjugate of each other. In this form, it's a bit difficult to tell. The trick is to do the second integral by parts. As we explained, integration by parts allow you to switch. So the trick is to do the second integral by parts. Second integral is this one. This is the first integral. This is first integral. So we do the second integral by integration by parts. As we explained, integration by parts allow you to switch the derivative from one factor in the integrand to the other. So we can switch integration, we switch the derivative from one part to another, the other. We can switch the derivative from one factor in the integrand to the other, as long as you change the sign at the same time. Therefore, the integral in equation 8.8 can be rewritten as 8.88 can be rewritten as 8.9. Now we just need to compare the two expressions in equation 8.7 and 8.9, which turns out to be easy. Because of the minus sign, it's clear that they are definitely not complex conjugates of each other. Instead, their relationship is captured by psi d phi equal minus the complex conjugate of phi d psi, which is the diametric opposite. I don't know what is diametric opposite. Diametric opposite.全くの完全の diametric opposite of what we wanted. Unlike the X operator, D is not Hermitian. Instead, it satisfies D だが equal minus D だが equal operator which with this property is anti-Hermitian. This is anti-Hermitian. Hermitian. Hermitian is D だが equal D. This is Hermitian. Anti-Hermitian. Although anti-Hermitian and Hermitian operators are opposites, it's very easy to go from one to the other. All you have to do is multiply by the imaginary number I or minus I. Therefore, we can use D to construct an operator that is Hermitian, namely, this is Hermitian. This is Hermitian. But D, this is anti-Hermitian. So if you have anti-Hermitian, you can construct a Hermitian operator by multiplying I or minus I. Here H bar is here in this case is just 1. If we look at the action of this new Hermitian operator on wave function, we find that minus IH bar d psi x equal minus IH bar d psi x dx. Keep this formula in mind. It will soon play a leading role in defining a very important property of particles, their momentum. Okay, is it okay? I don't know if anybody is listening. のSomeone is listening. Okay, I think someone is listening. It's okay. No, if anybody is listening. Okay, somebody. I go to the next section, the state of a particle. In classical mechanics, the state of a system, state of a particle, state of a system means everything you need to know to predict the system's future. In classical mechanics, okay. Given the forces acting on it. That, of course, means the positions of all the particles comprising the system, as well as the momenta of those particles. From a classical perspective, the instantaneous position and momenta are entirely independent variables. Classical particles, the instantaneous position and momenta are entirely independent variables. For example, for a particle of mass m moving along a one-dimensional axis x, the momentary state of the system is described by the pair xp. The coordinate x is the location of the particle, and p equal mx dot is the momentum. Taken together, these two variables define the phase space. These two variables define the phase space of the system. If we also know the force on the particle as a function of its position, Hamilton's equation permits us to calculate its position and momentum at all later times. They define a flow through the phase space. Given this, one might guess that the quantum state of a particle will be spanned by a basis of states labeled by position and momentum. Ket xp. The wave function would then be a function of both variables, psi of x and p. However, this is incorrect. We've already seen that things that would be simultaneously knowable in classical physics may not be in quantum mechanics. May not be knowable in quantum mechanics. Different components of a spin, say sigma z and sigma x, are an example. I'm sorry, I just don't do spin part. Okay, but I just assumed that the listener knows simple spin expression like sigma z and sigma x. One cannot know both components simultaneously. Therefore, one does not have states in which both components are specified. Why? One cannot know both components simultaneously, therefore one does not have states in which both components are specified. The same is true for x and p. Specifying both values is too much. Whether we are talking about spins, sigma z, sigma x, or positions and momentum, x and p, the incompatibility is ultimately an experimental fact. What then can we know about the particle on the x-axis? If not x and p, the answer is x or p. For according to the mathematics of position and momentum operators, the two do not commute. But I emphasize that this is not something you could have predicted in advance. It is the distillation of many decades of experimental observations. これ do not commute is like this, xp. This is not zero. Not zero. So x operator and p operator, xp minus px, it's not equal to, this is a do not commute. If the position of a particle is observable, if the position of a particle is observable, there must be a Hermitian. If the position of a particle is observable, there must be a Hermitian operator associated with it. The obvious candidate is the operator x. The first step in understanding this fundamental connection between the intuitive concept of position and mathematical operator x is to work out the eigenvectors and eigenvalues of x. The eigenvalues are the possible values of position that can be observed, and the eigenvectors represent the state of definite position. So next section, the eigenvalues and eigenvectors of position. The obvious next question is, what are the possible outcomes of measuring x, and what are the states in which it has a definite predictable value? In other words, what are its eigenvalues and eigenvectors? We will start with x. The eigenequation for x is x psi equal x0 psi, where the eigenvalue is denoted by x0. In terms of wave function, this becomes x psi x equal x0 psi x. 8.11. This last equation seems strange. How can x times a function be proportional to the same function? On the face of it, this seems impossible. But let's pursue it. We can rewrite equation 8.11 in the form x minus x0 psi x equals 0. Of course, if a product is 0, then at least one of the factors must be 0. But the other factor may be different from 0. Thus, if x is not equal to x0, then psi x equals 0. That's a very strong condition. It says that for a given eigenvalue x0, the function psi x can be non-zero at only one point, namely at x equals x0. For an ordinary continuous function, this condition will be deadly. No sensible function can be 0 everywhere except at one point, and be non-zero only at that point. But this is exactly the property of the Dirac delta function, delta x minus x0. Evidently, then, every real number x0 is the eigenvalue of x, and the corresponding eigenvectors are functions, we often call them eigenfunctions, that are infinitely concentrated at x equals x0. The meaning of this is clear. The wave functions psi x equals delta x minus x0 represents states in which the particle is located right at the point x0 on the x-axis. If, of course, it makes a lot of sense that the wave function representing a particle known to be at x0 is 0 everywhere except at 0. It of course makes a lot of sense that wave function representing a particle known to be at x0 is 0 everywhere except at x0. How could it be otherwise? But it is gratifying to see the mathematics confirm this intuition. Consider the inner product of a state psi and position eigenstate x0. Using equation 8.2, we get x0. How do you say? This is more like here, right? I think this one is more like this. Psi x infinity to infinity dx. So let me see. Let me see. x0 psi equal minus this way I got confused. I think this is just like this: psi x, x0, x dx. This part is delta x minus x0. I think this is it. By the definition of the delta function given in equation 8.4, this integral evaluates to psi. So this integral evaluates to psi of x0. Because this is true for any x0, we can drop the subscript and write the general equation x psi bracket is psi x. In other words, the wave function psi x of a particle moving in the x direction is a projection of a state vector psi ket onto the eigenvectors of position. We will also refer to psi x as the wave function in the position representation. Wave function in the position representation. So it's almost time. We start from here, 8 to 2. Next time, 255. Sorry, I wrote this one. This is just my memo. And please respond next time. So probably next time is like this. Tomorrow, Tuesday, 1 o'clock is next time. Then I will update. It's compass page. Here is the compass page. Then I update. Blue cap page. Here also I have a page. So I will update this for the next lecture. Then I will post. I didn't link this page, so I will. Hey, this is a little bit strange. Anyway, so I will give you the link to the tomorrow YouTube live. Okay, so thank you very much.